るとは思ってたけど。
でしたら運転していたトラックに堂々と名前が書いてあれば誰でも気づくでしょ。
いずれにしても一度話をしたいとは思ってた。
話すことなんてないわ。町の食料すべてを人質にしてそのまま済まされるとでも思ってるの？
私はあなたと同じフォースプログラムの出身よ。脳内インプラントとマインドパワーがあれば何だってできるわ。
マインドパワーとインプラントをアクセに使うなんて許せない。でもそれも終わりよ。
なのでも全ての終わりは始まりでもあるのよ。そうでしょう。ショーゴ、スプリンクルハットに来てそこで決着をつけましょう。
もういるわよ。
Hello, welcome to our video on how to construct an MO diagram for polyatomic molecules. To start, we'll learn how to do an easy MO diagram for a linear polyatomic molecule, which will be CO2. We first need to find the symmetry of the molecule, which in this case is d infinity h. But since the molecule is linear, for practicality we can substitute the d infinity h with d2h. Once we know the symmetry, we can find out which character table we need to use. Then, for the second step, we need to assign the x, y, and z coordinates to our atoms. The highest order rotation is assigned as the z-axis, and the molecules will bond this coordinate the way it is shown. For nonlinear molecules, the y-axis of the outer atoms would point towards the central atom, but this is not a linear molecule. The third step is to find the reducible representations for the balanced s orbitals on the outer atoms. When the outer atoms are not hydrogen, like in this case, the reducible representations for each need to be found for the outer atom orbitals. In this case, we have a p orbital of px, py, and pc, which will be used to find the symmetries of the group's orbital form. D2H has two folds of symmetry, so the reducible representations for py, px, and pc can be made separately. For oxygen, the E operation leaves oxygen unmoved, so we get a 2. For C2C, it is the same case, and we also get a 2. C2Y and C2X rotations move the two oxygen atoms, so there are 0 unmoved. Inversion also moves all the oxygens, therefore it obtains a 0 as well. Sigma xy bisects the molecule in half, so the oxygen gets reflected, leaving 0 unmoved. Sigma xc and sigma yc contain the oxygens in their reflections, so the oxygens do not get moved, therefore they get a 2. If you want, you can stop the video and work on the pc and px and py representations for practice, and then continue to check the answers. Okay, we will continue now. These are our representations. If you notice, we get a negative 2 for C2C. This means that the C2C rotation gets their orbitals flipped. We also obtain a negative 2 for sigmas, and when the sigmas obtain negative 2, that means that they are their inverse reflection. The fourth step is to reduce each representation from step 3 to irreducible representations. This will give the symmetry of the group orbitals. For this, we need to find the reducible representations that added together will give the irreducible representations. For S, it is AG and B1U. For PC, it is AG and B1U also. For PX, it is B2G and B3U. For PY, it is B3U and B2U. The fifth step is to identify the atomic orbitals for the central atom that match the symmetries found in the previous step. The central atom has an s orbital that is always Ag, since it is the most symmetrical symmetry label. The PC orbitals will have a B1U symmetry. The PX orbitals will have a B2U symmetry. The PY orbital will have a B3U symmetry. For the sixth step, we can finally start constructing the diagram. Since carbon has a higher energy, it will be higher and oxygen will be lower. We'll put the carbon on our left and the oxygens together on our right. Then we will combine the atom orbitals on the central atom and those of the group orbitals with matching symmetry and the similar energy to form molecular orbitals. The total number of molecular orbitals must be equal to the number of atomic orbitals used for all atoms. The two s orbitals form a bond as they have Ag and B1U symmetry. The PC also have Ag and B1U symmetry, so it forms these two types of bonding. Px has B2U and B2G, so B2U bonds with the B2U of Py, but the B2G cannot bond. Py has B3G and B2U, so B3G would be non-bonding and the B2U will bond. So when we put all together, we get the diagram.
Now that we know how to do the molecular orbital for CO2, it's time for us to do another problem for practice, but this one we're going to be using the H2O molecule. This is so that we know that nonlinears such as this molecule shown in the right hand of the screen can be determined by the similar process as used with the CO2. So for the first step, we are going to determine its point group. So we are very familiar with point group at this point because we've also seen it in class. So we all know that water is a bent molecule with a C2 axis through the oxygen right here and two mirror plane that intersects along the axis. So without me saying it, we should know that this molecule is a C2V molecule. So I know that the second step is for us to look at the character table specifically for the C2V, but for the purpose of keeping this slide together, we will be moving on to assigning axis to our molecule. So the C2 is chosen as the C axis. Why is that? So since O has the highest order rotation, it is assigned the Z axis right here, and the XZ plane as a plane of the molecule. We can see right here. It's also important to note that because hydrogen 1s orbital have no directionality, it is not necessary for us to assign axis to this hydrogen atom. And for the next step, we will be looking at this character table. So hydrogen atoms determine the symmetry of the molecule, and their 1s orbital from the basis of a reducible representation. So this one holds to be true. This is very true because it's what we're going to be using to determine what we have as the final irreducible representation. So if you guys want to practice, you can pause this video so you guys can do the character table. Okay, so the E operation leaves both hydrogen orbitals unchanged for a character of 2. The C2 rotation interchanges the orbitals, so each contributes to 0 for a character of 0. Reflection in plane of the molecule leaves both hydrogen unchanged for a character of 2. And reflection perpendicular to the plane switches the two orbitals for a character of 0. So this is going to be summarized in this table. So the representation can be reduced to the irreducible representation A1 plus B1 representing the symmetries of the orbitals, as can be seen here. So in step 5, these group orbitals will be matched with oxygen orbitals of matching symmetries. And what do I mean by that? So this is the hydrogen orbitals, what we also call the group orbitals, and this is the oxygen orbital, which we also call the atom orbital. And okay, for this one, as we said, the irreducible representation for the hydrogen orbitals is the B1 and the A1. But how did we get these? So the s orbital is unchanged by all operations, so it has the A1 symmetry. An s orbital is totally symmetric, as we can see right here. The px orbital has a B2 symmetry of the x-axis. Has a B1 symmetry of the x-axis, while the PY has a B2 symmetry of the y-axis, and the PZ has an A1. Okay, the PZ has an A1 has a oh my god, the PZ has an A1 right here because this one has the z-axis. So what do we have to do next? The A1 orbital, the hydrogen orbital, it's going to combine with the s and pz orbitals of the oxygen to form 3 molecular orbitals. This is going to be here. So it's going to be the energy level. This is going to be the energy level 1, 3, and 5. The energy molecular orbital 1 is only slightly lower in energy relative to the oxygen 2s orbital. 1, energy level 1, can be regarded as relatively non-bonding, and as expected on those bases of the relatively close energy match between the 2p subshell and the 3 hydrogen group orbitals, 3, energy 3, has a significant contribution from oxygen pz. 3 is a bonding orbital. And then we also mentioned energy 5. 5 is antibonding and has significantly more contribution from the oxygen pz relative to oxygen 2s. So we're going to go back to the last slide here. So the B1, the hydrogen B1 group orbitals combine with the oxygen px. We can see why, right? So like these and these would combine. The A1 is very symmetric, would combine to the S and to the PZ because of these. Okay, so as I was saying, the hydrogen B1 orbital would combine to the PX here to form 2 molecular orbitals, one bonding and one antibonding, namely these, the 2 and energy 6. As we can see, looking at these also helps on this side, also helps to determine why. So it's gonna form the energy level 2 and the energy level 6. The oxygen py, oxygen 4 with B2 symmetry does not match the symmetry of the hydrogen 1s group orbital and is therefore non-bonding. So the oxygen 2s orbital, it has a negative 32.38 energies, nearly 20 below hydrogen orbitals in energy. That energy we were talking about is negative 13.61. So it has a very little interaction with the group orbitals. The oxygen 2p orbitals are a good match for the hydrogen 1s because it has an energy of negative 15.85. Right? It allows the formation of bonding B1 and A1. When the 8 valence electrons are added, 2 pairs occupy bonding orbitals and 2 pairs occupy non-bonding orbitals. This complements the 2 bonds and the 2 lone pairs of the Lewis electron dot structure. So, as a summary of this, we got this molecular orbital diagram just by matching these characters, and these we got from the character table, while these we also got from here, and then we match them and then we can come up with this one.
So now we're gonna work on a more complex polyatomic molecule. In this case, we've chosen to work on NH3. We can now look for the character table, which in this case would be this one.
So for the next step, we need to assign the x, y, and z coordinates to the atom. Here, the molecule can be seen from the z-axis. And to appreciate the other coordinates more, this is the y and this is the x. Also, with the help of the character table, then we find the reducible representation for the 3 hydrogen atoms 1s orbitals. And since we have 3 hydrogen 1s orbitals, 1 H atoms will have A1 symmetry and the other 2 will have E symmetry. As already mentioned, that NH3 is a more complex molecule, and this is because it has more than 2 molecules attached to its central molecule. This is different from CO2 and H2O for that reason. Therefore, to obtain the group orbitals, we will need to address the projection operator method.
The projection operator method is described in our book as a systematic approach for deduction of group orbitals. In other words, it helps find out how atomic orbitals combine. First, we need to determine the impact of each point group symmetry operation in one atomic orbital within a set of identical atomic orbitals. For example, if we focus on our HA atom, we can see that the E operation leaves it unchanged. The C3 operation moves the HA to HB place. The C3 squared transforms the HA into HC. The sigma VA leaves HA unmoved. Sigma VB transforms HA into HC, and the sigma VC transforms HA into HB.
So the linear combination of the hydrogen 1s atomic orbitals that match the symmetries of A1, A2, and E irreducible representations are obtained. To do this, we need to multiply each outcome by the characters and add the results. For example, we multiply H1 times 1 from the character table and that gives us HA. We can also multiply HB times 1 from the character table and get HB. And this is going to be the same thing if we multiply HC from 1 from the character table and that would give us HC. So you will do that. You will do that with all the character tables. And if you want, you can pause the video and attempt getting all the linear combination. If not, this is what we are supposed to get. So it is, okay, now that you have all the linear combinations, they are added in this case. We will obtain 2HA plus 2HB plus 2HC. And for this one, 0 since they all cancel out. And for this one, it's 2HA minus HB and minus HC as seen here. So this is an important thing. And that the same general SALC can be obtained regardless of the initial atomic orbital examined. So HB or HC could have been the base atom instead of HA.
Since the result from A2 turned out to be 0, group orbitals of this symmetry cannot be obtained using the 3 hydrogen 1s orbital. The SALC for A1 shows that each 1s orbital contributes equally to this group orbital, but this is not the case with E. The sp orbitals of nitrogen both have A1 symmetry and the pair Px and Py has E symmetry. The nitrogen s and pc orbitals combine with the hydrogen A1 group orbital to give 3 A1 orbitals, one bonding and one non-bonding, and one anti-bonding. The non-bonding orbital is almost entirely nitrogen Pc, with the nitrogen s orbital combining with 3 hydrogen group orbitals for the bonding and anti-bonding orbital. The nitrogen Pc and Px orbitals combined with E group orbitals to form 4 E orbitals, 2 bonding and 2 non-bonding. So now we are almost done to the diagram. All we need to do is to combine the atomic orbitals of the central atom and those of the group orbitals with matching symmetry. And this is the diagram we would obtain. Thank you. I hope you understood it so that in the exam you can get a 10 on this. Have a nice day.